So very much in keeping with what Andrew was talking about earlier, I think we kind of all independently came to the conclusions that there's a little bit of a theme going on this year, which is it's kind of time to get a little more real. You know, we've floundered it for 10 years looking for ways to improve our propulsion, and golly, we haven't come up with some. I hope some of you took my class yesterday, and we went through some of those. So this is a mission I've been toying with for a long time. It's a 1,000-day U per year mission to do a transect of the Oort Cloud. I'll explain what that means. But regardless of how you do it, it's clear that we need some kind of mission for interstellar precursors. You know, to gather the funding to fly these missions, the folks at JPL have been laboring in the fields to do what they call an interstellar precursor, an interstellar explorer, for 20 years. The mission's never gotten funded because all there is to do is go out, and it's only interesting for people like us. You know, it tells you what the dust population is out there and what the particle and fields are doing, and that's all interesting stuff to us, but that hardly justifies the scale of mission expense that we need to get a flagship class mission done. We need not only to demonstrate relevant propulsion, but there's a host of associated problems when you start actually designing the mission. You know, why do you get your power and comms and navigate and all of those other things? And those of us in the field are really tired of hearing, we know we can't go to the stars because that would mean going faster than Voyager, and of course we can never do better than what we've already done. So any kind of big step forward would be a big psychological breakthrough that I think would be valuable. The Oort Cloud is what's out there. You know, we know essentially nothing about it. The entire history of the Oort Cloud, the science can be summed up by saying, well, we see long period comets, we assume they come from somewhere. We count the comets and we do models of what we think the probability is of a comet being perturbed into the solar system, and from that we make our estimates of what's out there. Then more recently, we noticed that, whoops, I hit the wrong button there. More recently, we noticed that we have these interstellar objects that are coming into the solar system now that our instrumentation is better, and we also assume those must come from somewhere. From that, the entire literature that we give the name of the Oort Cloud derives. How many objects are out there? Good question. How big are they? Good question. What's their velocity distribution? Good question. What's the dust environment like out there? Also a good question. These are, I mean, I could have shifted these curves up or down by at least an order of magnitude depending on which paper I drew the model from. But, oh my goodness, what wonderful technology. This happens to be from one of the papers in which Avi Loeb is a co-author. This is one of the many estimates for the Oort Cloud objects that are gravitationally bound to the sun. This is one of many estimates for the Oort Cloud objects that are just passing through the region of the Oort Cloud on their way from some other star system to some other star system. You add them up and you get this hypothesized population of Oort Cloud objects. For reasons I can't explain, the reference object is 2.3 kilometers. Everybody in the literature talks about the number of 2.3 kilometer objects. This is from another paper giving what we think the cumulative size number is. Again, that's based entirely on counting comets, and since we can't see small comets, we probably are underestimating the population of small bodies, and people try to make guesstimates for that, but we don't know by how much. So there's a lot of very fundamental scientific questions. I haven't done a formal survey, but I've talked to people who are in the space science community and people who look at the outer solar system, and the general reaction is, oh my God, yes, we'd love to know all this stuff. Except, of course, we have no idea how to do any of it, so we never ask for it to go on the funded missions list. So my purpose in giving this talk today is to start a little pebble of sand rolling that, God willing, will turn into an avalanche someday, of starting to convince people that a mission like this can be flown, and therefore scientists should start asking for it to go on the decadal survey list, because maybe we should start thinking about doing it one of these days. We'd like to know the number, we'd like to know the velocity distribution, we'd like to know something about their composition, which is expressed in the temperature, and we'd like to know a host of engineering questions that people like us worry about that are relevant to future interstellar spacecraft. What's the dust? Particularly, is there a long tail of dangerously large dust? What's the galactic-cosmic ray flux? And if we could get that far, we'd like to know something about the G cloud. In case you don't know, the Alpha Centauri system is not in the same interstellar cloud that the solar system is in, And it's hard to determine the properties of the next cloud while you're looking through the one that you're in. So we know very little about what the conditions like magnetic field and so on are in that cloud, and we'd like to know. But the Oort Cloud, the spherical edge of the Oort Cloud is 10,000 light years, 10,000 astronomical units away. Even the inner edge of this, so-called disk-shaped region or region in the ecliptic is 2,000 astronomical units to the near edge. Nobody knows where the outer edge is, but a consensus guess is about 40,000 AU out. The density starts to drop off again. 10,000 AU in 10 years is 1,000 AU per year. A Voyager length mission of about 40 years at 1,000 AU per year gets you to the outer edge of the spherical Oort cloud. 1,000 AU per year is an absolute floor of velocity if you want to do seriously think about going out and sampling the Oort cloud. And to put it mildly, 1,000 AU per year is a rather dramatic advance over the level of propulsion we've got right now. For many years, there was a mission called TAU on the JPL wish list, the 1,000 astronomical unit mission, that after 40 years would get to 1,000 astronomical units, and here I am proposing to do that every year. So obviously, propulsion is a big deal. And we do have alternatives. They're all low TRL, like everything in the interstellar field is, and so they have risk. And I want to make clear I'm not turning away from those in any sense. I am a co-author on this idea of dynamic soaring on the solar wind termination shock. And frankly, if I had my pick, that's how I do a mission like this. It's cheap, fast, and if we can get it to work, it should work very well. And you can also do it with an advanced fusion rocket, which we don't happen to have one of. But there's no particular reason we couldn't if we wanted to. I have this rule that if you're proposing to do something that you don't know how to do today, you should have 3 ways of doing it, because that way at least one of them might work. And my goal in giving this an alternative propulsion today is to talk about another one that might work. Just hit the spacecraft with lots of rocks. I think that's simple enough. Even a review board will be able to understand the physical principles involved. And this derives from work by Heller and company on the concept of putting out these little aerographite puffballs near the sun and letting the photon pressure of the sun push them away. And the concept being introduced today is instead of trying to turn those into spacecraft, we turn those into reaction mass. We let them hit the spacecraft and push the spacecraft away. It's kind of an alternative way of doing canned sunshine. You pipe the sunlight energy out to ever greater and greater radius by storing it in kinetic energy in these flying objects. So it's a 2 spacecraft mission. The one I call the Dispenser flies close to the sun and spits the pellets out. The sun very obligingly pushes them away, and the probe reflects the pellets off to get the suitable energy gain. And in rough figures, 1,000 AU per year is 1.6% of the speed of light. That should say 0.7 milligrams per pellet, not per probe. And that's over 1 billion pellets. So it's really better thought of as a hose than as a pellet launcher. It's sending out this stream of very low density mass. And also, clearly, with the number of pellets like that, they have to be generated in situ. You have to start with feedstock and blow bubbles. You can't possibly carry those pellets preformed. This is an artist concept of the dispenser with the sun off page to the left. This is Parker solar probe shield technology, but this is a 10-meter fairing. It could be adapted to a 9-meter fairing to go up on Starship. And this is the artist concept of the stream of pellets going away, which are the blackest things we know how to make. They're essentially carbon black. But when you're 0.04 AU from the sun, they still show pretty bright. So I would love to do a statite. And as many speaker about magnetic sails, I've done talks before on how you use them to do a statite close to the sun. And I'd love to do that. But my objective here is to come up with a technologically independent way of doing the propulsion problem, so it's no fair sharing common technology risks. So far, I couldn't do that, and one of the tricky bits is figuring out how the orbital mechanics of all this can work. The thing is, these pellets accelerate away from the sun so fast, they essentially leave on radial trajectories. It's almost a dead straight line leaving the sun, which means the angular velocity, the rate at which you tick off these angle lines, going around the sun has to initially match between the 2 spacecraft. But the further spacecraft has to be far enough away that there's time for the sun to accelerate the pellets. They can't be at the same radius from the sun. You wouldn't pick up any velocity. So to do that, what you have to do is do your Venus swing by, and then you come down here, and the dispenser does a retrograde burn to drop the apohelion, and the outer spacecraft does a prograde burn to raise the apohelion, and that gets the angular velocity around the sun at perihelion to match up. And then once you're lined up, you fly the probe into the stream of the pellets. Now, to get the number of pellets out in enough time that everything is happening close enough to the sun to perform this trick, you got to get the pellets out in about half a day. You divide the number of pellets by the amount of seconds that you've got, and you get about 35 kilohertz for the rate at which this pellets is coming out. This is not a trivial problem. And I'm not going to solve it here, a preview of coming attractions. I don't know how to do that. This is the miracle I don't know how to do yet. This is an animation to scale and to time of the spacecraft moving along. This is the dispenser, which I have no button here. There we go. The X is the dispenser spacecraft, and every white dot is 1 in 1,000 of the pellets being dispensed. And you can see what I mean about a radial trajectory. It's indistinguishable from a straight line, even though this actually is plotted in the right coordinates. So 1,000 times as many pellets as there are white dots on this picture are extending away in a stream. And again, you see what I mean by it's more like a hose than a stream of pellets. This is a little bit mathier than I probably need to get. Each collision, you have to aim the spacecraft after the collision to where the next pellet is going to be when you hit it. So if you just continued on unchanging, you'd follow the blue line, but since you're going outward to catch this next pellet, you have to angle the impact plate so that early in the trajectory you slow your radial velocity down a bit, because obviously you need more time to get all the way out here than you would have if you were taking the straight line. And then when you get late in the trajectory, you angle the plate the other way because you're getting farther from the sun. Your angular velocity around the sun has to increase, so you're picking up more and more prograde velocity to stay in the pellet stream as you go. Now the key point here, the first question everybody asks is, how do you aim the pellets? The answer is, you don't. The pellets are going to leave the sun on the hyperbolic trajectory that they like, and there's not a darn thing you can do about it. What you do instead is you steer the receiving spacecraft, the probe, onto the pellet stream, because we just need to hit the Oort Cloud. We don't care a little bit which direction we go. If we're plus or minus a degree, we're still in the plane of the ecliptic. The Oort Cloud will still be out there. So we don't care about this dispersion as long as we don't care about the slow drifts. What we care about is the random motion of pellet to pellet. That's the part that's hard to catch. How do you reflect pellets that are closing at 1% of C? You can't do it mechanically, or let's put it this way, if you did it mechanically, it would be a far from elastic collision. You do it electrodynamically. You ionize the incoming pellets, they pass through a grid, electrostatic grid, that reflects the ions back. The electrons are along for the party because they're so light. With pellets coming in every 30 microseconds, some kind of active system where you zap them with a laser or something like that is possible, but it struck me as very complicated. And I had a happy accident. As far as I know, this is the first time this has been put on paper, but I'm sure somebody must have thought of it before, which is to magnetically confine a low-density ion plasma forward of the spacecraft strike plate. The good news is the pellets are coming in so bloody fast. They just have to hit a handful of ions to produce enough energy to not only vaporize the pellet, but heat it up to its own ionization temperature. So you're talking about an argon plasma here that's on the same order of density that we use in plasma processing machines and semiconductor industry all the time. You know, it's like 10 to the minus 15 ions per cubic centimeter. So it can be confined with magnetic fields of very ordinary Gauss-type level intensity, not even Tesla level. So the pellets come in. It's like an aero brake for the pellets. The pellets come in, they hit this. It takes about 5 or 6 nanoseconds for them to thermalize. That means for the hot ions to hit other ions so that they all join the energy and share it. and then this more than white-hot expanding grid of carbon plasma decelerates in the electric field between this pair of grids, and this plate goes off the other way which it came, and thus is propulsion formed. So dispersion is obviously a big question. Always the first question, can you keep the stream on the target? We've talked about how we deal with slow drifts. Another issue is the pellets can't be perfectly uniform, so you have to spin them so that the slight non-uniformities average out. You have to spin them on an axis that's parallel to the axis they're flying on. And if that axis diverges a little bit, you get this thing called the Yarkovsky effect, which is that the hot spot is lagging a little bit behind where the sunlight is. So the re-radiation of its thermal radiation can shift you off in another direction. I don't know how big of a deal that's going to be. My back of the envelope estimate is we need about a microradian, which is not as bad as a microdegree, about a microradian of accuracy in speeding up the alignment. Can the machinery do that? I don't know. It's a challenge. The dispenser is a challenge. There are natural limits that we can't get better than. The sun is not perfectly uniform, nor is it perfectly static. It has these variations of sunspots. It has these variations from granules. You look at a picture of the sun, the corona is jittering around a little bit. Now the good news is we only care about how much that moves in about 30 microseconds, which is not very much, but not very much over a long distance adds up. I did my best I could from literature search to find out what the time period and spectrum of that variation was. The 3 sigma limit over a 1.6 AU time of flight, which is the farthest distance to the farthest pellet impact, looks like about 0.08 meters, which is quite nicely tolerable. And again, we have this huge advantage that we don't care what the slow drift is. We just care about the jitter. That's an example of trajectory here. You actually have the dispenser trajectory, but you can't see it because it's too small. It's a little yellow dot in the lower left corner. Over the course of our day, this is astronomical units in X, astronomical units in Y. The spacecraft follows that blue trajectory. The last pellet follows this hyperbola, and trust me, that is a hyperbola, not a straight line drawn with a ruler. It just looks like a straight line drawn with a ruler because the hyperbola is so flat. The acceleration starts out slow because we're close to the dispenser and the pellets haven't picked up much speed yet. As we move farther away from the dispenser, the pellets gets faster and faster. We pick up faster and more acceleration. At some point, we begin to outrun the pellets. And so even though the pellet speed is continuing to increase, our spacecraft speed is increasing more. So we get less and less from every pellet, and that's what causes that particular shape of the acceleration curve. This is an acceleration method JPL should actually like, because it's too much acceleration for humans. That's good. It only works for small spacecraft. That's good. And it involves fancy orbital mechanics, so they have something to do. So I'm praying that the gods that be might let us consider a propulsion method like this. The dispenser is really hard, and that's about all I can say about that. In no sense have I designed that machine. It's a very difficult machine to design. It has serious technological challenges, but let's be real, it's not on the same order as I'm going to invent a 500,000 second ISP fusion rocket. It's a difficult piece of mechanical design that I think a suitable engineering effort could tackle. Also, I'm not sure aerographite's the right material for this. The methods for making aerographite usually take some time to cook, and I'm interested in whether what we can do is just blow a bubble with carbon black in it, let the water go off, and be left with this bubble of what's essentially frozen smoke, and see if that can get the job done. Now, the big challenge. It's freaking dark out there. That is a rendering from Celestia of looking back at the sun in the direction, the spacecraft's flying towards galactic center. You're looking back at the sun, which is that quote-unquote bright star in the middle. This is Castor and Pollux. You're looking towards Gemini. So the sun's the brightest star in the sky, but not by much. It's about as bright as Jupiter is seen from Earth, and that's the only light in town. And people keep telling me, well, what's the big deal? We take pictures in starlight at Earth. We do, from 10 meters away. We don't take pictures from an AU away. And to detect enough objects to get a statistical sample of the Oort Cloud during this flight, as was mentioned earlier, these objects are far apart. You have to be able to detect the object when you're flying by about an astronomical unit away from it. And that is really hard. Bottom line is detecting it optically is hopeless. Why will it not go backwards? There we go. My own hope is interferometry. What you're doing there is detecting the black body radiation of the devices, which is at about 1 terahertz of the Oort Cloud objects. You have to distinguish it from the cosmic microwave background. You are slightly at a different spectrum than that, which helps by about 2 orders of magnitude. That still leaves you with about 15 orders of magnitude more noise than signal. This is not encouraging. But apparently, the astronomers have figured all this out, and it's well known in the field that a point-like object viewed from a distance looks like a diffraction pattern. It looks like a coherent source. And of course, the cosmic microwave background is an incoherent source. So I'm not an expert in this area, and I'm looking for a co-author to improve this part of the paper. But I dug through the textbooks, ran the formulas, and it looks like a distinguishable thing. If you turn everything to 11. That's the arrangement of the sensors. It's a set of wide-field horns pointed in all the directions so that you get three interferometry detectors pointing at every object in every direction of the sky survey. And then along the axis of motion of the spacecraft's moving, you can use synthetic aperture techniques to synthesize the very, very long aperture from the big movement. And another thing that's a huge help in the noise is any point-like source that's from cosmic sources doesn't have this gigantic parallax. When you're moving at 1,000 AU per year looking at an object an AU away, it's only in your field of view for about 10 hours. It's moving that fast. So the objects that are moving are the ones that you want to pay attention to. The objects that look stationary are noise that can be rejected from the algorithm. You also have to run the detectors and the preamplifiers very cryogenic. Otherwise, the thermal noise from them would swamp the signal. This is a pain, but to my surprise, you can actually buy now space-rated sub 1 Kelvin cryocoolers for instruments. So again, you have to do it superconducting, including the amplifiers. I'm not saying this is easy. It's not within the state of the practice, but in my opinion, it's at the edge of the state of the current art, not beyond it. You need power. It's got to be radioisotope. There's nothing else in town. It probably isn't plutonium because for a 40-year mission, it would be decaying, and you would actually need peak power at the end of mission, not the beginning of mission, to still stay in contact with people back home. Americium can do it, but it makes less power per kilogram. You have to use one of the various methods that people are working on, like thermophotovoltaics instead of thermionics, to get a lot more of the efficiency of the power source out so that you get more useful power per amount of radioisotope power. Again, none of this is new that people haven't been talking about. People have been talking about doing everything I said on this slide for 25 years. Nobody's ever gotten around to doing it because there's no flagship mission that requires any of it. Artist concept here of the dispenser, which truly is an artist concept. This is just tankage for feedstock and a notional volume to be synthesizing the pellets in before they get spat out the barrel of the gun. And then this is the notional spacecraft in its acceleration configuration with this big pusher plate assembly and the probe itself here. Once you're done accelerating, you dump the dispenser plate off and you're left with the probe. Whoops. Okay, there we go. This is a big Fresnel lens, 4 meters in diameter, so that you can focus the laser from 40,000 AU away and still be able to illuminate the Earth with enough photons to pick up. Even with all of that, it's like a tens of watt laser that you need to get enough bits per second to get the job done. And here you can see the backside of this standoff plate that all the RTGs are mounted on the far side of. That plate is there to keep both the thermal radiation and the gamma radiation away from the sensors. The sensors are insulated from the spacecraft body by the MLI, so they can be kept cool. Most of the interstellar space does most of the cooling for you. The cryocoolers do the last couple of degrees. And these are those horns I talked about, pointing in all directions to each feed a superconducting detector. There's more work to do on the propulsion system. The other alternatives have their own development needs. For this one, by far, the big thing to work on is the pellet producer. And for the sensors, lots of work to do. and I'm very much busy seeking a co-author, which I keep thinking I should be able to find at my local university, but I haven't found one who returns my calls yet. Oh, one more thing is that all these numbers I've given for size of sensors and frequency of detectors and all the rest of that is a case of my picking a point that seemed reasonable and seeing how the numbers go. One thing you'd really like to do to take this further is do a trade study to actually find out where the optimum point is for all of that. That work remains to be done. So what are the things I want you to take away? Number one, Oort Cloud exploration is a big deal. It would fill in a huge blank spot on our maps. I think the scientific community will generally agree with that if you can get them to stop giggling about thinking that it's okay to think about what a mission like this would involve. This is a no-kidding interstellar class precursor mission. You know, you're within a factor of 10 of a true interstellar velocity, and as far as the rest of the challenges on sensors and communications and power, it's all the same stuff we'd have to deal with for a serious interstellar spacecraft. And the discussion on where this should be on our list of scientific wish lists can't start until the scientific community thinks a mission like this might become doable. Otherwise, they aren't even going to start asking for it. And thanks to my artist who provided 24 hours ago all the great looking illustrations that you've just been seeing. There's my get off the stage chart. I'd really like to take this picture. That big Fresnel lens that we have pointing home when we're not shining a laser through it would make a great camera. And I'd really like to see what that would look like. And with that, I have time for a few questions, I think.
You only need 1,000 kilograms of pellets. Why do you have to synthesize them in solar orbit? Why can't you do them here at home?
I'm sorry, why can't I just what?
If you only need 1,000 kilograms of these pellets, why are you synthesizing them inside the orbit of Venus? Why don't you just make them here at home and put them in payload?
Because they're each a 2-meter diameter sphere, and the volume of them pre-deployed would be impractical.
I didn't get
carry
that
the. You have to carry them to 0.04 AU from the sun.
Yeah.
The sunlight to be strong enough.
Okay.
Okay. If they're each, let's call it 2 meters cubed.
Okay.
There's 10 to the 9th of them.
Okay. Okay. I didn't get the. I got the weight. I didn't get the volume.
Okay.
Okay. Thanks.
There's one back in the corner there.
So doing some rough back of the envelope calculations, the Oort Cloud is like 3,000 AU. Is that correct?
Well, the disc shaped part of it is like 2,000 or 3,000 AU.
So the newest solar sail proposals, like by Heller and Norte, or I forgot its pronunciation, but they propose getting 2% light speed if you do a very close-in sundiver. So a back-of-envelope calculation gives us 2.5 years to get there, if it was able to do that. Now, they would be small, quite small. So, I mean, it's not out of the ordinary that you can do it by a solar sail. You need to be able to do a very close sundiver. And
in fact, it's the same sundiver. The work of Heller is exactly what I based this on. Okay. These are the Heller pellets that we're talking about from his paper, as cited. But the problem is the weight of the pellet of a Heller class pellet is about 0.75 milligrams. It's hard to build a spacecraft out of that. It's especially hard to build a spacecraft out of that with a power supply that keeps it alive and doing science 10 or 20,000 AU away, and it's super double plus hard to send something like a kilobit per second of data back from a spacecraft that weighs micrograms. So the origin of this paper was essentially, my being excited by Heller's work and saying, how do we make a spacecraft out of that?